All here. Okay, so I would like to start by welcoming everyone to this session on neural networks and deep learning. And we are going to have 4 papers in this session. And as you know, the discussion will be at the end of the 4 presentations.
See if I can get this going.
Yep.
View, slideshow. Yeah.
Thank you. Yes.
Okay, good. All right.
All good.
Yeah, so good afternoon, everyone. Thank you for attending my presentation. You see a gallery of my collaborators here. The main author is Kiarash Zahirnia. We're both at the School of Computing Science. Kiarash is my PhD student, and he's in the process of moving from Vancouver to Montreal. So he's very busy, his internet isn't working. And so I said, well, I'd be happy to use the opportunity to present. We're talking about inferring latent edge types from relational data. It's just a bit of general motivation. Graph data are very important, very common. If you just think about all the relational databases that pretty much every modern enterprise has, there's been an increasing amount of interest on the deep learning side and many and growing numbers of applications. There's a current research frontier, which sometimes called latent graph inference, for example, by Hamilton from McGill in his textbook, where the idea is that you may not be given the graph structure explicitly. So in text mining, for example, one problem is to extract relationships from texts or from image data. A task is to extract a scene graph. And so I see our paper as being in that general context, but we're just doing a particular aspect of latent graph inference, which is inferring latent edge types. By the way, I can warmly recommend William's book if you want to learn about graph learning. Okay, so here's an example of a heterogeneous graph where you see different types of links, acting, directing. We usually use the term multi-layer graph. And it's known that you can and should use edge labels to improve graph representation learning. And giving one reference below here. Often this takes place in the setting of knowledge graphs. So we are looking at latent layers. So here's another example. If you take a friendship relation, say from Facebook, right? The data just tell you that, say, Lydia is friends with Sarah, Kevin is friends with Daniel. But really, if you even think just about your own Facebook friends, you have different types, right? So you have the people that you're friends with because they're classmates, the people that you're friends with because they're colleagues, people maybe sharing similar interests or in the same club. Okay, and so our question is, can we recover these different types of relationships? Okay, another example from the movie domain. So IMDb tells you the cast of the movie, but they don't tell you things like Tom Cruise is the star. And that would be useful, for example, if you wanted to predict Tom Cruise's salary in Mission Impossible. Okay, here's my one slide overview of variational graph autoencoders, which is the main model that we're focusing on. So you get as input a set of graph data of observed edge types. Then you run a graph neural network on the input graph, sorry. And you get back a matrix of node embeddings. Okay, so in goes a graph, possibly heterogeneous multi-layer graph, outcome node embeddings. And then the decoder takes as input node embeddings and reconstructs the observed graphs. Okay, so our proposal is to adapt this idea, adapt the encoder-decoder framework for latent layer inference. So we have a hyperparameter L for the number of latent edge types. Let's say that's 3. So then we run the encoder 3 times in parallel. And combine the three different encodings into a single set of node embeddings. And then similarly in the decoder, we run the decoder 3 times or L times in parallel. And then we reconstruct the observed links as a linear combination of the inferred latent links. Okay, so an observed link is viewed as a component consisting of components where the components are latent edge types. This is similar in spirit to using multiple heads in attention models, if you're familiar with those. Okay, I'm just pausing because that's it. Okay, so we're not introducing a new architecture. We're introducing more a framework that you can apply to any graph encoder decoder setup. And so we evaluate what happens when we do for some 6 state-of-the-art variational graph autoencoder models. And we do qualitative embeddings, and then we look at 2 downstream tasks to get quantitative scores. To get ground truth edge type labels, we do this homogenization operation. So let's say you have an IMDb, you know who's acting, you know who's directing, and then we remove these labels. So now we get a simple homogeneous graph. And then we run our latent layer inference on this homogeneous graph here on the right to see if it can recover the types on the left. Okay, so what we're looking at in this visualization is representing pairs of nodes, which we call dyads. Just for a bit of context, there's a recent trend in graph representation learning to work on, to go beyond node embeddings and work on embeddings of pairs, triples, sets of nodes. I'm giving you a reference for here from NeurIPS 2021. And there are both theorems and empirical evaluations supporting the importance of working with pairs and triples of nodes. So our latent layer inference approach actually gives us a novel way to represent pairs of nodes. And the idea is, suppose that we have our latent edge types, like let's say 3. Let me go back to this diagram. So now our decoder will give us, for every pair of nodes, for each of these 3 latent edge types, it will give us a probability, the probability that these 2 nodes are related by this latent edge type. Okay, so we get 3 probabilities. It's like a mixed membership model. And so we can use those 3 numbers for 3 edge types as the representation of the pair. Okay. So that's a really low dimensional representation. As a baseline, we said, okay, the obvious thing to do is when you have a pair of nodes, well, you have an embedding for each node separately, you can concatenate the 2 embeddings. That will give you something like 2 times 128. And so now we're in this diagram, we're comparing these 2 embeddings. So every point is a pair of nodes, and the pair of nodes is labeled blue if it's unlinked nodes, or red or green if there is a link between the nodes, but and then they're linked according to the type. So for example, on ACM, a red dot means that we have a paper subject pair. And so the thing to compare is the top versus the bottom. So DGL FRM is one of the standard autoencoders, a very strong performing one. And so if you add latent layer inference to this and use our new dyad representation, you get a cleaner separation of the classes. Similar for DLP. So at the top is just the concatenate node embeddings. At the bottom, we have the latent layer inference dyad representation. For IMDb, the separation is probably not totally clean for either method, but we are separating blue versus non-blue, which means existing links versus non-existing links. Okay, so that's for visualization. Now we're going to talk about 2 downstream tasks. So one is link classification. So in this task, you're told, okay, Tom Cruise is related to Mission Impossible, John Woo is related to Mission Impossible, but the question is, how are they related? So is Tom Cruise an actor or a director? And that's really a key evaluation for us, because the goal of our system is to reconstruct the edge types. So, we want to do well on this task, and I wouldn't be here if we didn't. So if you compare again VGAE or DJL FRM, so standard method, and then we just add our latent layer strategy, then VGAE, you go from 63 to 82. So this is micro F1, just think of it as F1. Graphite, you go up by 30 points. So these are really big improvements for classification type accuracies. So this is, I'm pleased to see that. So we also did link prediction. So link prediction says, okay, there's Tom Cruise, there's Mission Impossible, and can you tell that Tom Cruise is participating with Mission Impossible somehow? And I know this is a lot of numbers, but the takeaways are, again, if you compare, for example, graphite versus graphite LL with latent layers, you go up by 0.3 points in AUC. If we compare basic VGAE from Velling, you go up 0.5 points in, sorry, what am I saying? You go up 5 points in AUC on this scale. So we get substantive improvements, even on these data sets that are quite saturated, where really almost all the methods are in the 90s. And then the other thing here is, for context, we give you SEAL, which is a state-of-the-art link prediction method that has quite a different strategy from the node embedding strategy of the autoencoder methods. And even there, basically, SEAL will beat the standard autoencoder methods, but if you strengthen the autoencoder methods with latent layer inference, it becomes competitive. Not, sometimes better, sometimes worse. Okay, those are takeaways. All right, let me summarize. So inferring latent graph structure is one of the big open areas and directions of current research in graph representation learning. Our paper addresses an aspect of that task, which is to infer latent edge types. The basic idea is to start with an encoder-decoder architecture and run L parallel encoders, decoders, one for each latent edge type. We showed that we can use the inferred edge types to provide a new dyad representation, a new representation of node pairs that seems to match ground truth edge types very well. And for downstream tasks, we substantially improve link classification and also link prediction. All right, thanks very much for your attention.
Okay, thank you very much, Oliver. Very, very interesting presentation.
You're so nice, Paula.
Thank you very much. No, it's really a very nice work. I have several questions for you, but we can talk about that at the end. Yeah. So let's continue with the third paper, which is, I think the presenter is Hamed Mozaffari, and the paper is detecting flashover in a room fire based on sequence of thermal infrared images using convolutional neural networks. So a long title, yeah. But it seems also very interesting work. So please, Hamed, go ahead.
Sure. Hello, everyone, and thank you for listening. So I'm presenting our work here at National Research Council of Canada about detecting flashover using deep learning. So first, the question is that what is flashover and why it is important to predict it. So it's a one dangerous phenomenon when we have fire in construction. So specifically around the year, for example, in USA, 30,000 firefighters get injured each year because of just fire-related accidents. And one of the most important phenomena that happen in fire incidents is flashover. It means that, what's the flashover? Flashover means that all the combustible materials in the room are suddenly ignited near simultaneously. So for example, here you can see from left to right, if you check the timing of the video, it only less than 3 minutes it takes time to a room completely without any fire reach to completely full of fire. So we call this phenomena as flashover. So it is important that we don't have flashover always. I mean, sometimes it happens, sometimes it doesn't. So it depends on the size of the room, size of the opening. It depends on materials which are burning in the room. So for this reason, there is no any absolute criteria for flashover prediction to just check and say, okay, we have no flashover. But under some standards, we can guess the happening of flashover. So for example, in a standard ISO 9707, which has a standard room size, and the flashover will happen when the upper smoke layer in the room reaches to the temperature of more than 600, or heat flux. It means that the energy that the smoke make for the floor is upper than 20 kilowatt per square meter, and heat release rate between 1,000 to 2,000. So it's just a roughly criteria. So to detect flashover, which is really dangerous for firefighters, previous studies focus on using sensors. So we can put lots of sensor in a room and then monitor the temperature, monitor heat flux rate, and this kind of stuff. But the problem is that we need first data. Just by using data from one room, we cannot generalize the idea for other fire incidents. For this reason, many researchers also use simulation data using computational fluid dynamics, and they could propose some machine learnings to predict flashover in fire incidents using sensors. But this approach, it is not really useful for firefighters, because in any room fire incidents, firefighters cannot go and install sensors in the middle of fire when the timing is just less than 3 minutes. And this is one of the drawbacks that thermocouples and heat flux gauges have for predicting and monitoring of the flashover. So to solve this problem, we equipped the fire rooms, or we employed thermal imaging cameras to monitor the situation for flashover prediction. So we use lots of methods like monitoring the temperature using thermal information, but that's not giving us all the criteria we have in flashover prediction. We have only focused on temperature. So for the first time, we use deep learning, specifically convolutional neural networks, to consider the flashover situation in real time as a binary classification of flashover and no flashover situation. It means that we consider the whole fire incident into 2 subcategories: the flashover region, and the rest is non-flashover. Sometimes, as I mentioned, in one room fire, maybe we have no flashover at all. Maybe the opening is small, the fuel is not enough, or there are other items that we will not have the flashover at all. So we selected ResNet model because it has a good performance in previous studies, and we hyperparameter tuned for our database, and then we reached to ResNet 18. And so our data set has 6 different videos we captured from real actual fire incidents at NRC, and we use 4 of them for training and validation and 2 for testing. One of the test video doesn't have flashover happening inside, another has a flashover. So in total, the number of frames from each video, these videos are from thermal imaging cameras, are limited. So for this reason, we increase the number of this data set using augmentation, and then train the model to distinguish for us the difference between flashover and non-flashover situations. So for example, in these 2 test videos, the right one is the case that the room has no flashover, and the left side is the case that the room has flashover incident. So they are so similar in terms of data distribution, and I will explain later the problems we have. So there are lots of statistical analysis in the paper we will publish in this conference, but visualization of our results is that if we follow the data from sensors for the test data with flashover, the deep learning model can predict flashover around 71 seconds or even more before the actual flashover, and it increases the probability. At the same time, for the case that we don't have any flashover incident in the room, it shows some part of probability, but the amount of probability is less than 50% or so, and it can completely detect that this room doesn't have any flashover. So the accuracy of model in average F1 score was 84 and accuracy was 91% for just this data set. As a conclusion, this was the first use of deep learning using thermal infrared imaging technology as a non-invasive test approach for actual room fire test to predict flashover incidents. Our method was fully automatic end-to-end, and it can be embedded into embedded systems for using by firefighters in near future. Thank you so much for listening. For any question, please contact me at this email.
Okay, thank you very much, Ahmed.
You're welcome.
This was a very nice talk. Okay, so we will need to have the discussion at the end. So we will continue with the next presentation, which is, I think, Garima Malik, the presenter.
Yep.
Okay, and the paper is software requirement specific entity extraction using transformer models. So Garima, please go ahead, the floor is yours.
Thank you, Paula. Hi, everyone. So my name is Garima Malik, and I'm the PhD student in TMU University. And our paper is software requirement specific entity extraction using transformer models. So this is my presentation overview. So I'll start with some basic introduction, then some background study, then we'll discuss the methodology and results, following with conclusion. So what's our problem statement? So basically we want to identify the software specific named entities in software requirements, which are extracted from SRS documents. And these SRS documents are attributed or extracted from different disciplines. So basically what SRS document is, it's basically a record or a documentation where the developers write the functional and non-functional requirement, or maybe the list of requirements for a product and what it used to expect, or what in a way the product used to behave. So we have all the list of functional, non-functional, user interface, hardware, software, all these kinds of requirements available in SRS document. Now it's pretty important because SRS is a rich information text. So it's pretty important that you identify some important keywords or entities from this text, which can be pretty useful in all the NLP downstream tasks. So the techniques we employed in this particular work is we fine-tuned transformer model checkpoints over the data sets we extracted. Then we also compared the performance with probabilistic machine learning models. And then we also did some preliminary experiment with few-shot learning, which is like the newly popularized concept. And in terms of expected output, so if you can see, there's a requirement which says the AVRI shall support autonomous mission plans as well as pilot-directed flight. So probably AVRI will be an actor in the requirement, then support will be the action performed in the requirement. Autonomous mission plans and pilot-directed flights, they're just property or maybe describing a particular requirement. So this is the expected output from the entity extraction task over requirement specification. So the research motivation. So as I mentioned, SRS documents are highly rich and structured text, and it's pretty important that if you want to, and these are long documents as well. So if you want to present a high level overview or summarize these documents, so entity extraction can help you in that. Then we have some similar and dissimilar requirements mentioned in SRS documents. So entity extraction can also serve as a feature set to discriminate between similar and dissimilar requirements. Then we have, requirement quality assessment systems, which basically, measure whether a requirement is particularly good to have in the system or not. So we can use these entity extractions or maybe named entities as an additional feature input in RQA systems, which can improve the efficiency of RQA systems. And then additionally, we can also train some more machine learning models with requirement text and software specific entities as features for various NLP tasks, such as requirement classification or maybe SRS document summarization or document clustering in SRS documents. Then what we contributed in terms of this paper. So we trained one machine learning based conditional random field model specific to the software data set with the custom feature set named as MLCRF. Then we also fine-tuned some transformer checkpoints for within software perspective, like these famous names, Bert, Roberta, and Albert. And we also did some detailed numerical study and entity level error analysis with our 3 distinct annotated requirement sets. And we also investigate whether like few-shot learning capabilities work in the software specific domain or not using this text-to-text language model BART. Okay, so starting with background study. So very few studies are there which, basically apply named entity recognition as a task in software domain or maybe in requirement engineering domain. The studies listed here in software specific nerd category, they all are basically, trying to find the software specific entities in Stack Overflow post or Stack Overflow text. So the data is basically social media content, but nobody is, trying to achieve the similar task in SRS documents. So probably that's the novel framework we are proposing here. Then in terms of few-shot learning nerds, so we did see some of the new techniques applied in few-shot learning. So few-shot learning basically means when you have small data set and when you have like less labeled instances. So with those less, with those few labeled instances, how can you, make state-of-the-art results? And maybe how can you train all these transformer models? So that's basically a few-shot. So in few-shot learning as well, all the data sets and the problem statements are pretty generic. So nobody tried few-shot learning in software domain as much. So we are using this template-based BART model, which is the text-to-text model, and then basically trying to, translate a named entity recognition task into machine translation task. So that's the working flow of our NER model. So we start with some raw requirements extracted from SRS documents. Then we apply the annotations and we basically try to tag these as BIO tagged input. So BIO tagged stands for B is the beginning of tag, I is the inside tag, and then O is no tagging. So as you can see, the requirement is the UAV shall fully charge in less than 3 hours. And the tagging says DA is not an entity, then UAV is an actor, and it's a beginning of an actor tag, so it's indicated as B actor. Then shall fully charge is an action, then less than is an operator, mathematical operator, then 3 hours is a matrix. So we basically approach this problem within, with two directions. One is, handcrafted feature engineering with MLCRF learning, and the other one is with transformer models, which are black box, obviously. So you just apply word piece tokenization and feed into transformer models. And with the MLCRF learning, you just first extract, some handcrafted features. So basically you deep dive into data set and, see some rules which can be, pretty beneficial to lead to a particular entity. And then you can apply those rules in terms of dictionaries and feed into MLCRF learning model. Then you post-process your data set after the predictions and then get the BIO tagged output. In terms of data sets, we had 3 different data sets. One is DORS data set, which stands for Dynamic Object-Oriented Requirement System. So this is basically a task management system. And then we extracted some short user stories and software requirements from this. And this graph basically represents the frequency of entities we found in this particular data set after annotation. So verb and I can say user is the most dominating ones. So in total, we had like 5,000 requirements after pre-processing data cleaning. So we end up getting like 3,333 with 10 entities. Then on the right-hand side, we have SRE dataset, which stands for software requirement entities. This dataset is a mixture of multiple SRS documents, which attribute to different disciplines such as aerospace, transportation, medical domain, healthcare domain. So we extracted or sampled some of the requirements. Then we annotated those datasets with these 6 main entities, starting with actor, action, object, property, operator, metric, and then basically feed into the models. Then we have the last data set, which is RQA data set. So we have requirement quality assessment system provided by IBM in the IBM cloud as well. So this is a system which basically, before, keeping entry of a requirement into a system, it basically checks for the quality. So basically tags 20 different entities from the system, and these entities are pretty extensive. It covers both linguistic and morphological structure of the requirements. I'm just showing here 8 frequent entities we had in our data set, but we experimented with all the 20 entities. Then in the experimental setup, as I mentioned, the NER models, we used 3 models, and the validation strategy was threefold because DORS was pretty, good in terms of numbers, but SRE and RQA was limited. It had only 378 requirements. So that's why we employed threefold only. And this table, as the highlighted row suggests you. So for the DORS data set, BERT large case model works pretty well. And then, basically, outperform the MLCRF. MLCR are expected to perform well because we have handcrafted features there, but still BERT large case performed pretty well. So that's a thumbs up for us. And then for SRE as well, BERT large case performs pretty good in terms of F1 scores and precision and recall. But in RQA, since we had 20 entities and 378 requirements, so for some of the entities we had 0 support. So that's why in that case MLCRF is working pretty well compared to all the other transformer models. Then in terms of error analysis, so initially in the literature, people only use classic NER matrices like precision recall, F1 score to basically, measure their performance. But we actually did some error analysis. So case 1 and case 3, as you can see. So with classic NER matrix, you can only, account for case 1 and case 3, but for partial entity matching or for, boundary matching in entity extraction task, we don't have any matrix. So, I guess back in 2013, in semantic evaluation conference, they produced or they basically introduced some error matrix, and then we used the same error matrix to identify our model prediction or did the error analysis in our models. So the error analysis basically suggests that, NER models on these data sets, they miss 5%, 8% and 29% entities in these data sets respectively. So this missing percentage, explains the data shortage or maybe, so data distribution. So with DORS, we have abundance of data. So here we are missing very less number or less percentage in the entities. And it is increasing when we have more number of entities and less number of requirements as well. And basically, we tried to calculate these correct number of entities, incorrect, partial, and missed entities with all these data set with the best model, which I just showed on this particular table highlighted in the blue color. So, and like moving towards few short learning results. So we tried, starting with training with few number of samples. So you can see with 16% of training set, few short template model is giving us a very good accuracy, and which is a great news for us because usually we don't have much data to train our models. So in case of that, we can apply few short learning. But as you can see, if you use full training set like 100%, then probably your fine tuning BERT model will outperform the few short template model, and which is obviously possible because fine tuning BERT has more capabilities than few short template. But still, for it's simple, efficient technique. For fewer sample, you can apply few short learning. So in terms of conclusion, I can say that like our fine-tuned transformer based NER model showed promise in identifying the software specific entities, and few short NER model proves to be a sample efficient technique for lower number of samples in the training set. In terms of future scope, we're trying like, can we apply some advanced few short learning methodologies for software requirement data set as we have less number of requirements? And we can also apply some data augmentation techniques to improve our data sets to tackle the minority support problems. So thank you very much. And I'll be happy to answer all your questions.
Thank you very much, Garima. A very nice presentation. I think right now is the time for the questions. So if anyone is in the audience or any participant online, you can write it on the chat. You can raise your hand if you want. Now would be the time to discuss. And if not, maybe I can start with one question. So not really sure where to start. So Basil, maybe by the first paper. So Basil, that was a very interesting presentation. And I do have a question. So you used non-IID data there, right?
Exactly.
So how was that generated in your different tasks? Because you used a non-IID setting for generating the different tasks. So can you tell us a little bit more about how you simulated those?
So can you hear me? Yeah.
Yes.
So the task, for example, in CIFAR, for example, so we have a data set of CIFAR 10 and CIFAR 100. So this was separated. So like the first task is all the tasks of CIFAR 10. And the remaining task is, for example, the second task is the 10 first classes of CIFAR 100 and so on.
Okay, okay.
So we also have an ImageNet 15 dataset where we have like 10 classes per task, for example.
Okay, so are the classes are the classes uniformly distributed in the first one in CIFAR 10, and they are, right?
Exactly. Yeah.
The classes inside each task, they may or may not be uniformly distributed. Like
this is exactly the point. Yeah.
Okay.
Yeah.
Okay. Thank you.
You're welcome.
And I just have another quick question. So you mentioned the phi value that plays a role on how much you give to the two components of your model, and the phi, how difficult is it to tune that phi? Because you want it to forget but not too much, or you want how difficult it is. And did you notice that it's task dependent, like or domain dependent?
So it's really depend on the number of tasks that you have. So for small number of tasks, this is not like much difficult to tune this hyperparameter. But when you have a data set like Omniglot, for example, where you have a lot of tasks, where you have, for example, 20 or 5 or 25 tasks that you have to learn in sequence, then it might be challenging. to find good parameter that will allow the model at the same time to perform well on the task he has already seen, and also to have enough capacity to learn the upcoming
to
task.
continue learning,
Yeah.
because you know in the beginning how many tasks you are going to learn.
Exactly. Yeah.
So maybe you start your tuning, the range of the tuning from that point, right?
Exactly. Yeah.
Okay, makes sense. Thank you very much.
No
I
problem.
was just curious. So maybe I now jump to Oliver. So let me try to remember. This is more difficult this way with all the discussion at the end. But
yes.
so,
latent edge types.
yes, I remember. I wrote some things here. So I was curious. It's a very interesting work. But honestly, you actually proposed at least three different solutions, right? I was looking at the dyad representation, and I was thinking, could that be also used as an unsupervised method to do classification? The dyad representation that you proposed.
Yeah, in general, I mean, yes. I mean, it is unsupervised in the sense that all we know is the links, right? We don't know the types. Yeah, it's just when you say classification, in our experiments, we have ground truth.
Yeah, but I'm just thinking as an alternative way of an alternative application, right?
Mm-hmm.
You could actually try do you think that makes sense to use the dyad representation as an alternative way to, if you don't have the ground truth, as a way to build clusters and.
Yeah, no, it looks like it should work as far as I can tell. So that's a nice.
Okay.
Yeah. So.
And another question I have is related to the possibility of enriching other graphs.
Mm-hmm.
So do you think that your solution could also graphs that do not have some characteristics, and you could actually generate a bit of feature engineering on adding more information that you could infer to other graphs? You think that would be?
Yeah. I think that's what I have in mind, really.
The future?
Yeah. One place where people do that a bit is, say, video analysis. Like, so it's easy to extract relations like, oh, this object is on top, right? You have spatial relations. And then you say, okay, I think that the objects that are close to each other are interacting. But I think our method could be used to try and learn to say, yeah, but what type of interaction, right?
Mm-hmm.
So two horses beside each other are interacting in a different way from a person on top of a horse, right?
Exactly. So I think it's a very interesting and promising direction.
Yeah. So that's the main place, exactly. But I think I think in the Facebook example, it's very plausible, right? We all know that we have different types of friends. So I have the intuition that this sort of latent structure is very common. So.
Yeah, and extrapolating that and enriching other contexts with this inferred layers, it should be I think it's very promising. Okay, congratulations on the paper.
Thank you.
Okay, so I don't see any questions, so I will just continue with the next.
Oh, I have a quick question for Basir. Basir, how is continual learning different from online learning? Is it because you have different tasks, or am I missing something else?
The only difference is that in online learning, the tasks arrive on the fly, so you might not know how much task will come. So you don't know the number of tasks in advance. But when we refer to continual learning, generally it also, so we can say online learning is a part of continual learning, because continual learning also have the case where you know the number of tasks in advance, but you want to sequentially learn them.
Okay, right. So it's probably something if I never change the task, then it would kind of degenerate. Yeah. Okay.
Yeah.
Okay, Paula, sorry I interrupted.
No, of course, this is for the participants, not for me. But I can continue now with, I think, Ahmed. So Ahmed, I think your paper is also very interesting. You provide a solution for a critical problem. So my question is a bit related to that too. So if you have a model for this kind of urgent situations, you want it to be fast. So if you evaluate it, you have some idea on how fast it is, how quick you can get the performance of your neural network?
Yes, I can answer your question in terms of frame per second. In inference time is around 20, but it based on the hardware we have. I mean, the GPU, CPU, it depends on that. So at the current version of the work on the computer, we can increase the frame rate with using more hardware facilities, and or even shrinking the size of the data, like a smaller size of images. But in future, we need to think about this more, because we are going to move the same idea to the embedded systems. In that case,
yeah, but if I'm sorry, I cannot hear you anymore.
Yeah, so specifically it's a 25 to 30 frame per second.
Okay, but reducing the size of the images might be a problem, right? You might lose performance.
So, you know, as I mentioned in the slides, the problem here is that there is no specific criteria by eye. If you look at the no flashover, you cannot distinguish a lot. So this is one of the problem we have.
They're very similar, right?
So definitely larger is not a specific feature.
I'm sorry, I don't know if it was just with me, but I couldn't hear you.
No, he cut out with me too, yeah.
Okay.
Oh, okay, so sorry, I think that. So do you have my voice now?
Yep.
Yes. So you were saying that you're talking about the image size?
Yeah, so I just want to say that there is no specific feature in a specific location in frames that we are looking to say that shrinking the size of image has impact. So it's just a trend of the frames is a feature here. So yeah.
So maybe the size would be a good trade-off, reducing it to obtain more speed. Okay, so there is a question on the chat to you also, Ahmed. So where did you get your data about the fires? Is it a public data set?
No, unfortunately, this is not a public data set. We have two projects. One is in 2010 and 12. The NRC conducted. The name is CFMRD, if you like. I think the report is available on the internet, but the data set is huge. I mean, I don't know how they can publish or not. And recently we did the same experiment just specifically for Flashover. We haven't published that yet, but maybe that become publicly available soon. So in parallel to us, NIST, the National Institute of Standard and Technology in USA, have similar data set with a collaboration with NASA. They are working on the same thing. Some of their videos are available for public.
Okay, that's good. Thank you very much. That we are always looking for data, and when it's kind of challenging.
Yeah, I know.
Thank you very much.
You're welcome.
So there is another question from Erfan. I wanted to ask Ahmed about the temporal relationship of the images. I wanted to ensure that the model doesn't capture that type of relationship between data points. Any comments?
Yeah, that's the thing that we are working on, that using temporal data in the frames. So it's the current project that we are doing. We just reported without considering that temporal data. For sure, there is temporal information in the different frames, But the important thing is that the temperature of we are looking is 600 and more, and it is difficult to capture videos using thermal imaging cameras that has a maximum temperature of 400 usually on the market. So for this reason, this temporal data can be useful in RGB databases. That this is the current phase of our project. I'm working on that.
Okay, thank you. Any more questions from the participants? And because I think we are a bit over time, I would like just to say, Garima, this was a very interesting, the last presenter, this was a very interesting presentation. And I kind of am not surprised that the CRF model is doing well. So maybe a small question for you would be, does it compensate actually to move from CRF to another more complex model like BERT, or because it will be much more time consuming and CRF will be very quick?
Yeah, probably because CRF has probabilistic training methodology, so it's quick, but probably in SRE and DORS data set, which we had, BERT provided like 3%, 4% improvement over MLCRF, so that's fine. But in case of, very few requirements and large entities set, MLCRF works pretty best because they are extracting handcrafted features. So that's why, yeah.
Okay. Thank you very much. Very nice work.
Thank you.
Thank you. Okay, so I think there is another question to Dr. Schulte. I wanted to know your opinion on using your method to extract partial relationships in images for better image classification, possibly. And before continuing, I think we can have the answer to this, but I would also like to ask all the participants if they want to continue to discuss, to join the Gather Town, which is available for everyone after this session, and to continue the discussion there. Okay. So I don't know if we still have Dr. Schulte here. And I don't think so. So Ervan, maybe you could try to join the Gather Town and see if you can catch up there. Okay, thank you very much for all your questions, for your participation, and I hope you're enjoying and continue to enjoy the Canadian AI Conference.
Thank you.
Thank you.
Thank you, Paula.
Thank you.
Bye.
Bye-bye.
Bye.
To Jordan to start the recording. Hello, everyone. Welcome to our afternoon session here. I'm pleased that we're going to be able to continue on with the range of things we've been seeing here. So my name is Fred Popowich. I'm a professor in computing science at Simon Fraser University. That's out of Burnaby in British Columbia, joining you today from Edmonton. And for our session here on AI applications, we have four long papers. So, and we have all the presenters in the room. So the way that it's going to work is we're going to have the four presentations, and then after the four presentations, we're going to open it up for questions. And so hold your questions, as during the presentations in terms of that. And feel free to also use the chat if you want to communicate to me during the session. And then just a reminder ahead of time is at the end of the session, I'll remind everyone again, we can join each other in Gather Town. It's not the same as being in person, but it at least allows us to socialize a bit more. So with no further ado, let's start with the first paper, which is going to be presented by C. Lin, which is on stacked bidirectional LSTM for predicting emission of nitrous oxide. Over to you.
Okay, thank you, Professor. Good afternoon, everyone. Today, I want to present the stacked bidirectional long-term memory for predicting emission of nitrous oxide. I'm Lin. I'm the third-year PhD student from the University of Ottawa. Okay. Firstly, I want to give you some introduction about the background and the motivation of this research. And then I will give you the some knowledge about the non-short-term memory. And then the data retrieval and preprocessing will be mentioned in the model 3. And then the simulation result will be presented in the tables. Finally, I will give you some, I will summarize the paper and give you the conclusion. Okay. Firstly, why we choose the neutral oxide as our study object? Firstly, because neutral oxide is the greenhouse gas, and it can absorb heat 300 folds higher than carbon dioxide, and it is the main culprit for stratospheric ozone depletion. So the neutral oxide have a great impact on our lives. So we like to study the emission of the neutral oxide in the agricultural practice. And traditionally, we're using a lot of methods from the machine learning field to predict the emission of the neutral oxide, such as multi-level perception, the support vector machine, the random forest, and the non-short-term memory. And I see the process of the emission of the neutral oxide. Actually, you can see that we can describe the emission of the neutral oxide in a simple using simple differential equation and accurately to describe the whole process. So that's why we choose the neural network model to predict the neutral oxide, because it is a black box. And in this paper, we're choosing the non-short-term memory as our neural network model to predict the emission of the neutral oxide, because it can handle the sequence data. And this is the architecture of the non-short-term memory, and he have 3 gates: the forget gate, the input gate, and then the output gate. And he have a consolidated memory here. And we combine these cells. We combine these pairs, and then we form a bidirectional non-short-term memory, which can process the data forward and the data backwards. So we can have a bidirectional information. This is the architecture of the bidirectional non-short-term memory. And for the data collection, because we have 4 chambers, the data is collected by the recall equipment, which encased in a protection box, and then we put the sensors in 4 different places for serving as different farming practice. We place the chamber 1 on an uncultivated area where the dirt has not been cultivated for approximately 40 years. And we place the chamber 2 on the straight road using the more fertile stripping, and the chamber 3 is placed on the straight road using conventional fertile stripping, and chamber 4 is placed on a patch of the field that has broadcast the fertilizer applied and worked in the top 3 inches of soils, which is also called a conventional broadcast cropping. And this we're using this formula to calculate the neutral oxide flux, where this Fn neutral oxide is the soil neutral oxide flux, and the V is the chamber volume, P is the atmospheric pressure, R is the gas constant, S is the soil area, and T is the temperature. So this is the formula we used to calculate the neutral oxide flux. And since the data, the data we get, it have different units and have different scales, so we have to normalize it. So we're using the min-max normalizing approach to minimize to normalize the data between the range -1 to 1 or 0 to 1. And then the normalized data could be represented by a vector using NT. NT is called the neutral oxide flux, and the T is the temperature, W is the water flux, the timestamp T. And then we combine all these vectors together at different time step together to form a matrix, data matrix. Then we input this data matrix to the non-short-term memory model to predict the emission of the neutral oxide. And this is the results we get. from the prediction using the LSTM to predict the emission of neutral oxide, we can see that the blue line is the actual data, and the yellow line is the predicted data. We can see that the predicted data actually can follow closely to the actual data. Yes. And in order to measure the performance of our model, we're using 4 measured metrics: the mean absolute error, the mean absolute percentage error, the rule mean square error, and the R squares. For the first 3 major metrics, I think we can see from the formula, if the value we get is smaller, the better the performance, right? For the R squared, if the value we get is close to the 1, the better the performance, right? More closer to 1, more better, better the performance. Okay, the SI here is the observed emission of the neutral oxide. SI hat is the predicted value, and S bar is the average value. And this is the result we get from the simulation using the, and we run the models 10 times to get the data. So in order to avoid the stochastic factors that exist in the model, and then we calculate the average value and the standard errors. In the table 1, we can see that we compare the MLP and the bidirectional non-Schulte memory, because MLP is a static method. It just our model, bidirectional non-Schulte memory, is a dynamic model. So here we can see that non-Schulte memory always outperform the model of MLP. In all 4 major metrics like this one, the IMSE, for LSTM, it just have 1.836 plus minus 0.029. But for the MLP, he will get a larger value in the RMSE matrix. And then for other, for the MAE, the value we get is the 0.0893 plus minus 0.025. But for the MLP, it's have a large value, right? So we can see as for all major metrics, and our LSTM is outperform the MLP. And then we also study the different timestamps, how different timestamps to impact the model's performance. We can see that the LSTM model is not quite sensitive to the timestamps we choose. But we do the experience, for 1 timestamp, 3 timestamp, 12 timestamp, 24 timestamp, 48 timestamp, and 96 timestamp. We can find that in the range of 3 timestamp to 24 timestamp, the metric is doesn't vary too much. So we choose the 12 timestamp as a good timestamp for us to predict the neutral oxide using the bidirectional non-Schulte memory. And we also studied the influence of different hidden nodes on the model performance, because the hidden node here just represents the complexity of the model, right? So in order to avoid the overfitting of the neural network model, we adopt the early stop technique to avoid the overfitting. So theoretically speaking, at the more complex the model, the more accurate results we will get. But we need to make a trade-off between the computation efficiency and the performance, the accuracy. So here we can see that so we choose 100 hidden nodes as a good hidden node. the number of hidden nodes to approximate the emission of the nitrous oxide. Because the 200 hidden nodes will cost the longer time to train the model. It is low efficient, low computation efficiency. But from at least from the we choose 2 hidden node, 5 hidden node, 20 hidden node, 15 hidden node, and 100 node. We can see that when the more and more hidden node added into the model, although the accuracy is become the model is become more and more accurate. When the number of the hidden node beyond some first values, the added accuracy is low, is so trivial, right? And between the 100 hidden node and 200 hidden node, we can see the accuracy didn't change too much, it didn't increase too much. Okay, and then we also
should be wrapping up right now here. So you have one more minute
for
wrap
I will end this soon. Okay, thank you. I will also study the influence of number of features on the model performance. We found that the 2 features, which is the nitrous oxide flux and the temperature, can get the best results. Which means in our case, the water flux is sufficient, so it doesn't impact the the emission of the nitrous oxide so too much. And then this is my conclusion. In processing sequence data, long-short memory is performed better than MLP, SVM, and other machine learning approach. The LSTM model is still quite sensitive to test rate. So optimal number of test rate is ranged from 3 to 24. And with early stop technique, the overfitting is naturally avoided. So we need to take a trade-off between the computation efficiency and the performance of the model. So we choose 100 hidden node as a good choice for our model. And in this study, we found that the most related features are nitrous oxide flux and the temperature. As for now, the optimal configuration for long-term memory is 12 times staying, 100 hidden node, 2 features. Thank you. Merci beaucoup.
Merci. Thank you very much. And thank you for finishing on time there. That's great. So as I remember, I mentioned to other people, we'll have questions after all 4 presentations. So it's my pleasure then to introduce the second presenter here. So I'm just going to, thanks for stopping your screen share. So the second paper today is going to be presented by Dakota Soares. And he is going to be presenting a paper on the Huffing decision tree-based approach for soil classification, with the disclaimer that he will have to leave this presentation, leave right after his presentation. So we will hopefully have his supervisor available to answer questions afterwards. But over to you, Dakota, for your presentation.
Thank you, Professor Fred. Hopefully you all can hear me okay. And I will get underway here. Yeah, so as Professor Fred said, I'm going to have to slip out, but if you have questions, you can talk to my supervisor, Dr. Lee. He is here. In addition to emailing me, you can reach me at my Fanshawe email. I'm a professor at Fanshawe College, and the Athabasca email as well, which is there. Just a quick note about me. I'm a full-time software developer, and this was my undergraduate thesis by project, I guess you could say, my final computer science project back when I was in undergraduate studies. I'll be going to University of Western Ontario for a master's in engineering. Anyway, let's continue on here. So my project surrounded a Huffing decision tree approach to soil classification. So let's just start with the kind of why classify, why would we classify soil? Well, there's lots of reasons to classify soil. The biggest reason is in terms of soil management. So soil classification, classifying your soil is very important when it comes to a lot of agricultural. The agricultural industry regularly classifies soil because you can obviously grow different types of things on different types of soil. In a lot of geotechnical surveys, you can build different things on different types of soil. So being able to classify soil accurately is very, very important. And Following from that, who defines soil classification? Well, here in Canada, the NSSC is kind of a governing body that classifies soil. That was created by the government of Canada back in the early 1900s, if memory serves me correctly. And they have a book called the Canadian System for Soil Classification, which is in its 3rd edition, and that has been out since the 1980s, where they specifically outline the classifications of soil. Before we continue into the problem statement itself, I just want to give you kind of a brief sketch of what a pedon is, because that kind of surrounds this discussion of soil and sort of how we take a measurement from soil in and of itself. So a pedon is basically just a 1 meter square area of soil. So it's a cubic square, and we have different horizons in that pedon. So you got your A, B, and C. Each of those represent a different area of soil, and those tied together give us a unique soil classification, of which they're outlined in the soil classification handbook. So what's the problem here? Well, industrial soil classification programs, they're inaccessible to a lot of users. So my thesis kind of surrounds a practical element as well as a theoretical element. So my goal here was to look at classifying soil and look at the research literature around that, but at the same time implement a solution in terms of a programmatic solution to this problem. So went around looking for what's out there as it stands for programs, what's out there for research. So currently, programs are very inaccessible for users. There's far too many options, and they require specialized equipment or personnel to operate. A majority of them are developed primarily in the USA, and there's quite a bit of literature actually on Indian soil classification as well, because the US and India are major wheat exporters and importers. Obviously, they don't adhere to our Canadian system of classification, which render them unusable in our instance. Soil classification in and of itself is a niche market, and so solutions are obviously limited. Theoretical literature on the subject is even worse. Robertson is kind of the de facto guide for classification using penetrometer data, and Bhattacharya et al. Outlines various algorithms to classify subsoils. Both are somewhat helpful. However, that's pretty much the gist of soil classification literature. So not entirely helpful, but able to extrapolate some results from that to be used in my own research. So current practical applications in terms of what applications actually allow someone to classify soil. Well, there's a few. Gaia's WinSev is prohibitively expensive, unfortunately, and very specialized. Geosystems CL Suite is similarly priced to Gaia, and it only includes the USDA classification, so not RCSSC. The USDA soil data viewer is free, but it's outdated, and obviously with mobile apps coming to the forefront in the last decade or so, those unfortunately are non-existent when a lot of farmers or technicians, engineers out in the field who would maybe want to take a sampling of soil accurately cannot do that from their smartphone or tablet or mobile device. So what should the solution to this problem be? So basically, again, just to recap, the problem here is we have a whole bunch of range of soil testing applications that are prohibitively expensive, and we need a quick and accurate result from soil testing that we can start analyzing. And if we have to go and get a proper geotechnical report or a more comprehensive geotechnical report done, that is fine. But there is a solution that is cost effective to be able to accurately get the soil classification and be able to make a preliminary judgment off of that in order to, is it worth going and doing a comprehensive soil analysis? Is it worth the money to do that? So the solution has to be portable, it has to be cost efficient, accurate, and easy to use. The data cannot consist of PCT, which is penetrometer cone testing data, because, well, a penetrometer is expensive and a lot of users don't have access to that, and it costs thousands of dollars to operate. So for user simplicity, the options must be finite. So what we did is, the solution here is machine learning, obviously. So the program, it must be easy to use, it must be portable, and gives the user detailed classifications based on the choice of soil attributes using a machine learning algorithm. The program is meant to obtain a preliminary classification that can be verified later via, as I mentioned earlier, geotechnical means through a laboratory. So the data set that we used to kind of give, well, there's one main data set, and then we're applying a couple algorithms to it as well as bringing training data in. So we have our pre-built input with our training data and our data attributes. Then we take our user enter data, we feed that all into the algorithm, and you've all been obviously tipped off to which algorithm is the best here. And then we get an output, which is a soil, grade group, and an order. So that's kind of a simple kind of data flow in how we went about solving this problem. So data attributes, they come from our handbook. Our training data lists the optimal data attributes, which are also taken from the handbook. So we've got data attributes which are from that handbook, but then the handbook also describes what are the optimal data attributes for that particular soil classification. So that is also included. Then we have a user enter data, which the user is like, okay, I go outside, I'm looking at this, I dig a hole in the ground pretty much with my backhoe, take a look at 3 feet of soil, this is what I'm seeing, this is what I'm going to input into the algorithm. We take all 3 of these inputs and we come up with a grade, group, and an order. So test results, well, we chose 6 algorithms initially to look at when taking all this data and formulating it. The J48, which is off of Quinlan's ID3 tree, the random forest, and a bunch of Bayesian networks, and then the Hafting tree, which is also a decision tree. Hafting tree came out on top in all of our results. So you can see here the TP rates for the different algorithms tested. I wanted to keep this rather concise and easily understandable for the time that I've been given. So we can see pretty clearly that the Hafting tree, on average, performs better. So we're talking our validation here. So just, I should probably clarify that for our graph test results. So our green line is our test data as used as the training data. Our 70-30 split is our blue line, and our tenfold validation is our red line. So that's where you're getting those our horizontal axes from. Then our vertical axis is our TP rate expressed as a percentage of accuracy. Essentially, I'm kind of wording it simply for time's sake, but you kind of get the idea. And the report, which is on my website, would have further details into how all of that is outlined. So the solution. So we got a theoretical solution there. So we got our prototype. Well, we got our theoretical algorithm that is going to be best used in this scenario. But we also wanted I wanted a prototype. I wanted something that I could kind of implement and kind of play around with. So the data set and the algorithm were implemented as a Java application. And the program directs the user to answer a series of questions from this data. The algorithm is used to calculate the grade group and the soil order. So think of a fancy survey, if you will, though I wouldn't want to boil it down to just that, but that's essentially what it is. It can't be done in a web browser because remember, the back end of this is a machine learning algorithm. So it's not as simple as your JavaScript or HTML survey form. We use Weka on the back end for our Hafting tree. Test cases in the program. So we tested in the program versus testing the algorithms. We're about an 80% success rate, which is feasible in my personal opinion for what we have. And this is kind of an idea of what the program looks like. So it's fairly straightforward. I'm not a GUI person by any means, but we get the idea. Where the user can take this out on the laptop, take a look. It's very simple. Remember, we're focused on the theoretical here, but we're also focused on the practical as well. So it's simple for a hobbyist or a farmer to go out. They can pick their soil colors, their predominant horizons, and up in the information menu, which I don't have a screenshot of, it gives some helpful guidelines to whether what a biome is, what a soil color could look like, and so on and so forth. So, conclusion. Well, obviously, the Hafting tree algorithm was the best at deciphering the data, and the application prototype is simple and it gives an accurate result. And the prototype gives us an example of how a solution to a problem could be realized. there's a bunch of further research that one could do. You could develop a mobile application. There's a couple other issues that I found that could be rectifiable. But all in all, for an undergraduate research paper, I had a lot of fun with it. And yeah, that concludes my presentation. Thank you.
Great. Thank you very much, Dakota. And thank you very much for finishing exactly on time. Well done there. Yes, you're getting even applause from the back, virtual applause from the background there. So that I know you have to head off now. So again, everyone, please save your tough questions for your supervisors who are going to be able to answer them afterwards. We're going to go on to the third paper right now, which is going to be presented by Marwan Yassine. And the paper is entitled FIJO, a French insurance soft skill detection dataset. Et merci Marwan, et c'est à vous maintenant. Merci.
Merci, thank you. Thank you all for being here. So as Fred rightfully pointed out, I'm going to be talking about FIJO in French, or FIJO in English. And if you're wondering what that stands for, it's basically an acronym, which stands for French Insurance Job Offer. And as the title of the paper suggests, it is a data set for soft skill detection. So during the presentation, we're going to talk about the data set itself, what we chose to do with it. So spoiler alert, we're doing skill detection, as well as the future directions in which we want to take our work. But before all that, let's talk about the context in which the project was developed. So the project is actually a lot bigger than what I'm going to present to you. It's a multidisciplinary project with business administration, ethics, and education proportions. And it's about the study of the impact of the modern technological transformation on jobs, and more precisely in the insurance industry. So how is the growing implication of technology and software, everything that comes with that, affecting people's jobs and the skills required to actually perform those jobs. And it's a project that focuses on jobs with a high female representations, which is basically due to the fact that the jobs that are mostly affected by the transformation, whether it be clerical or administration type jobs, are dominated by women. So we're focusing on that. And it's also a project led by the Future Skills Center of Canada, and as well as a few insurance company partners. So let's talk about the motivations of building a data set. First of all, our team's part in the project was to study this from a machine learning perspective, and we chose to do that by detecting skills within job offers, because we thought it would help try to establish trends and how the skill descriptions, how the skill demand is growing more and more during the years. So that's basically the first motivation. The second is the fact that manual analysis is very time consuming and very costly, especially when you have a lot of job offers with different languages and with different requirements, with jargons as well. Thirdly, there are very few public data sets regarding job offers, and even fewer annotated and none in French. So I don't know if well, it's in the name, so FIJO is French, and the dataset is in French. And this is mainly due to the fact that there are intellectual property barriers. So usually a company would choose not to disclose their job offers so as not to establish trends that would help their competition, basically. So the dataset itself is constituted of 867 job offers that come from basically 4 insurance companies that are partners of the project. They're situated between 2009 and 2020, so there's a lot of time coverage. And the dataset is also de-identified in order to protect the interests of said companies. When it comes to pre-processing, we haven't done much, just basic removal of some punctuation and some inconsistencies within the data set. But as far as NLP pre-processing is concerned, we kept it very simple, and we basically stayed very close to the original job offers. So I'm going to present a few statistics of the dataset itself. As you can see, we have an average number of words per offer of 300, so usually long, mid to long offers, but there's a very, very high standard deviation. As you can see, the distribution here, it varies a lot from offer to another. And also we have a few outliers here, as you can see. Another interesting thing to notice is the lexical richness, which is basically the ratio of the number of unique words per offer divided by the total number of words. So this basically indicates to what extent the lexical or the vocabulary, if you want, that is employed within an offer is varied. So here we can see there's a very low lexical variety. There are a lot of swap words which can contribute to this, but as far as you can see, even from a qualitative perspective, there's not a lot of variety in a job offer, which is quite understandable because a job offer is not a novel. So you wouldn't expect to be a lot of different words in an offer. So in and of itself, the annotation part is necessary. So what's the annotation? In order to do what we want, which is the soft skill detection, we needed a labeled data set since we wanted to approach it from a supervised learning standpoint. So what we did is we chose 47 random offers in order to annotate, and we split them into sentence groups. So basically, since we had limited time and limited resources to do the annotation, instead of considering one offer as a data sample, we split it into different sentence groups and we consider each one as a sample. This enables us to have a total of 499 data samples, and it was manually annotated by an expert. So in all, we have 4 soft skill groups: thoughts, results, relational, and personal. The 2, I think everyone can understand. The first 2 might seem a bit weird, but this is due to the fact that it's a translation from French. So thoughts is pensée for those who speak French, and results is résultat. And if you want an idea, you can check out the data set. You'll have a better idea of what each one stands for. So as you can see here, we have the number of data samples per different skill. And as you can see, we have quite an imbalanced data set with the thoughts and personal skills dominating and the relational and results coming last, especially the results. And when it comes to the skill lengths or the length of each skill, you can see here that it's generally quite small, but we do have quite a bit of a variance here, and we have quite a lot of outliers as well, which as we can see, or as you can see if you check out the paper, can really make the learning process difficult. The third chart here is quite interesting. It depicts the distribution of the words classified by different skill type. And as you can see here, there's quite a lot of overlap. There are certain words that can be easily identified or easily attributed to a certain skill type, but in general, there's a lot of overlap, which complexifies the learning process even more, as we'll see later. So now let's talk about the automatic skill detection task, which is the gist of what we want to do with the data set. We encountered many challenges, 2 of which I've already enunciated: the class imbalance and the lexical overlap. There's also the fact that soft skills are not very easy to define, even for a human being, as opposed to hard skills, which are usually technical skills, something very easy to identify. Soft skills can be something like related to emotional intelligence, for example, or collaboration, things that are not very easy to identify and not very easy to separate, to classify. So a particular skill can easily be confused between personal and thoughts, for example. And this is something which we're actually struggling with currently, because we're trying to improve on our data set. We're trying to bring in more annotators and sort of enrich what we have already. And we're struggling with this even with human beings. So you can imagine how hard it might be for a machine learning model to learn how to classify these skills. Another challenge that we have is from a grammatical standpoint, and I'm sorry for the non-French speakers, but basically here we have three different tokens. We have two skills here that are of the same type and are separated by conjunction. Here the A is the AND conjunction. And if you look here, we have the same type of skill, but the conjunction here is part of the skill itself. It was annotated as part of the skill. So it's not quite easy for a model to find patterns within the data sets. So this makes the learning process even harder. Let's talk now about the models that we used for the task. We used 3 different models, 2 different architectures. The first of which is a bi-LSTM, and it has been presented before 2 presentations ago, but basically it's a recurrent neural network. We use fast text embeddings, French embeddings, since the data set itself is in French. And as you can see here, basically we are encoding each word in a sentence, and then we are running them through an LSTM and obtaining the class predictions in the end. So if you want more details about the architecture, you can check out the article. And as I'm sure a lot of you are familiar with LSTMs. The second architecture we're using is Camembert, which is a transformer network based on the Roberta transformer network, for those who are familiar, and which itself is based on a very famous BERT transformer encoder. So I'm not going into details of how these networks work, but you can check out the corresponding articles, which I would greatly recommend, since they've revolutionized the world of natural language processing. But basically it's the same. We have tokens in the as entries here, and then we're doing some processing here, and we have having actually hidden states. We have representations of the encoders. Then we run through a classification fully connected network to have the corresponding classes predictions. So we have 2 configurations of these particular networks. We have a frozen network. So we use the network itself as a frozen language models to obtain representations and then to do the classification. And then we use a configuration where it's unfrozen. So basically we fine tune the entire thing to see what gives. When it comes to experimental setup, it's really quite regular for a deep learning project. So we have 5 random restarts, 5 random models that we train for each architectures, 300 epochs with learning rate scheduling and early stopping. Quite regular 80-10-10% data split. For the Camembert and frozen, since the transformer networks tend to have a bit of instability when learning, we do a bit of learning rate warm-up that we experiment with as an additional experiment to see what if it can enhance the stability of the model, and we'll see a little bit later if it does. And what we do as well is try different training subset sizes. Since we have limited data, we're trying to see to what extent, especially for the pre-trained models, to what extent do we need to give them data in order to have good performance. And last but not least, which is a quite important point to make, is the fact that we have token-wise metrics, even though we are in a task that can be compared to named entity recognition, for example. We focus on the tokens, and this was basically due to time and resources constraints, but we're trying to make that better.
If you could wrap up within the next minute, that would be great.
Yeah, I'm almost done. So as we can see here, the Camembert and frozen model, which is basically the model that we fine-tuned completely, gives the best performance, which was basically expected. We can see the bi-LSTM coming in a bit last, and we can see the instability that I talked about a minute before. As we can see, there's a lot of standard deviation. And by the way, this table presents the mean accuracy and standard deviation per model. And we can see as well that the warm-up kind of mitigated a little bit, but did not really solve the instability of the model here. And we can see that Camembert frozen is the most stable model. So for more details and a more in-profound analysis, you can check out the article. And for future work, as I said, basically we're trying to enrich the data sets, have more annotations, try to implicate more annotators, do perhaps a little bit better pre-processing, and go into a more skill-wise scheme rather than a token-wise. So that's basically it. If you want, I have the links here, the article, all of the code is publicly available and the data set as well. And if you have any questions, I'll be happy to answer them in the allocated time slot.
Merci, Marouane. And we're going over to the final presentation so that we will still have time for those questions at the end. So turning it over to Syed for his presentation on an empirical study on probabilistic forecasting for predicting citywide electricity consumption. Over to you, Syed.
Okay, I cannot share my screen.
Oh, we have to stop the share screen from Marouane. Okay, you should now be able to, hopefully. Yes, it says, there we go. Yep, there we have it.
Yep. Sorry.
Go ahead.
Thank you. Hello, everyone. Good afternoon. I'm Syed Rafael. Today, I'm going to talk about my work named an empirical study on probabilistic forecasting for predicting electricity consumption. The co-author of this paper are Dr. Mucahit Cevik and Daria Kichi. First of all, I'm going to give you some background information. Efficient energy management is important because it helps to control energy consumption, reduce demand, can save electricity cost for the customers, and also reduce environmental damage. That's why accurate electricity demand forecasting is more essential, because it plays an essential role to project the future needs as well as helps planning increase electricity needs. For getting accurate electricity demand forecasting, previous study mostly focused on deterministic models. However, probabilistic models forecastings are important for carrying more information, provide more opportunity for efficient production planning. After reviewing most related and recent study, it is noted that the most common time series method categories are persistence method, which is known as the naive predictor, physical models, time series linear models, AI-based model, which includes the ML-based approaches, and hybrid model. Several studies proposed a variety of methods for electricity demand forecasting using time series data and the statistical models like AR, MA, Garima, and also machine learning and deep learning approaches. To the best of our knowledge, multiple time series of city-wise electricity consumption were not used in the previous study. We applied a state-of-art global forecasting method named Deep AR, Deep State, on multiple time series. And a detailed numerical study has been done, compare a large number of forecasting methods, consider both point forecasting and probabilistic forecasting performance. We consider various classical methods as well as complex architectures for our study. As a naive baseline, we considered the lag value as a predicted the value at the future time step. We use a seasonal autoregressive integrated moving average with exogenous variable is a Serimax as a representative statistical forecasting method. As a machine learning model, tree-based ensemble techniques are focused, especially GBR and random forest, which are shown to be effective for time series forecasting. As a deep learning models, we employ RNN named LSTM and GRU, which are particularly suited for time series forecasting, as they have the ability to capture long-term dependency through gates and cell states. As global probabilistic forecasting models, we consider Deep AR, Deep State, which support multiple time series as input and generate global forecasting model. Deep AR is trained the model which is based on autoregressive recurrent network architecture. The model is autoregressive because the observation at the last step, this one, JED, uses as an input, and it is recurring because it uses the previous output of the network. The likelihood, this one is a fixed distribution whose parameters are given by the function theta of network output is h. Deep state method for probabilistic forecasting was designed to address the limitation of two generic forecasting method, state space models and deep neural networks. Deep state is able to incorporate structural assumptions for forecasting even with a small time series, while the traditional state space models such as ARIMA and exponential smoothing can only succeed in these tasks when the data is clearly understood with enough history. On the other hand, similar to deep neural network, deep state is able to learn the complex pattern of similar time series by extracting higher order features of larger data set. In this study, Turkey electricity data is used, which was published by Energy Exchange Istanbul Transparency Platform. It has 5 years data. There are two data sets. One contains hourly total energy consumption, and another data set contains a percentage use per city for each month. For numerical study, hourly total energy consumption data is split into 81 distinct time series. This figure shows the 10 days samples of time series for selected 5 cities. We extract the month, day of year, and day of week, and hours value from the timestamp as a covariate for our study. For our experiment, we apply 90-10 training test split over our data set. We consider 3 different prediction horizons, namely 6 hours, 12 hours, 24 hours for test set performance evaluation. We employ commonly used matrices to access the forecasting model performance. Especially, we consider the normalized root mean square error, the normalized deviation, and the symmetric mean absolute square error matrices. For probabilistic forecasting, we use the weighted scaled pinball loss at the 0.05, 0.25, 0.5, 0.75, and 0.95 quantiles. We perform detailed parameter tuning experiments to identify ideal parameters for forecasting model. The scikit-learn, the Gluon test package, and other Python library used for our implementation. This figure represents forecasting performance of all the models. Forecasting performance are evaluated by using NRMNC matrices average over 81 cities. GRU and LSTM is as a deep learning model perform constantly well, and their error don't show too much variation. Both models outperforms all other models, including naive baseline and Serimex model. As a tree-based ensembles models, RF and GBR provide nearly similar prediction performance and predict better for longer prediction horizon. As a global forecasting models, DPR and deep state model perform worse than other deep learning and tree-based ensemble models. This figure illustrated the predictions on a single random test samples over all traditional forecasting method for 2 cities. RF and GBR show similar performance and can more accurate mimic time series patterns compared to others. The detailed performance value for point forecasting prediction over 3 target cities are provided in this tables for the 24-hour prediction horizons. We observe that GRU outperforms all other models. LSTM LSTM performance is almost close to the GRU. The error boundaries of GRU and LSTM are marginal and constant. We also find that DPR and deep state perform slightly worse than GRU and LSTM, but perform substantially better than all other models. Probabilistic, this table shows the probabilistic forecasting results for 3 selected cities for 2 different prediction horizons. Overall, deep learning models outperform all other models, especially GRU shows the best performance for all prediction horizons. RF and GBR perform almost similar. As a global model, like global models, a DPR deep state shows a better performance at 24 hours prediction horizons. These figures illustrate the prediction results for the sample time series for DPR deep state as a two global forecasting model, as well as GRU and RF model. All 4 models perform better at the beginning of the prediction horizon than at the end of the horizon. We note that in most cases, GRU is able to capture the ground truth within the 50% forecasting interval. However, we find the global forecasting model provide the lowest level of ambiguity in the probabilistic prediction. We can conclude this work as DPR and deep state model have slightly lower performance than LSTM and GRU in terms of point forecasting performance, as the global forecasting model method do not lead the meaningful performance gain over simpler model, because the sample structure of the database structure is simple, and DPR deep state models show better performance of longer prediction horizons, considering the quantile loss value. DPR and deep state model can be considered for electricity power generation planning that accounts for worst case analysis and stochastic scenario generations. This includes my presentation. Thank you for listening. I'm glad to answer any question if you may have.
Great. Well, thank you very much for your presentation and for finishing on time. So we have 6 minutes for questions, formal minutes for questions, and then we have to go to the gather town for more things. So let's, just so that it's equitable and everybody gets a chance, are there any questions relating to the first paper? And if not, I'm going to ask questions. So any questions for Lin? Just turn on your video if you have a question. Okay, so my question for Lin was, you talked about using you used 4 different sensors and you explained where they were and what motivation for them. Had you considered using more and having more factors, or going more than the 4?
Consider for using what?
You had used 4 different sensors when you deployed it. Had you considered using more sensors, and were there any other things you wish you had measured instead, or in addition to those 4?
Yes, but more sensors means more money, right? So we will consider using more sensor to measure more data, and then yes, this is our future research.
Okay.
Yeah.
Okay, that's great. So money is always a limitation in terms of
yeah.
Okay. Although Dakota's not here, are there any questions on the second paper that Ali might be able to? So again, turn on your video if there's any questions on the second paper. Before we go on to that one, so give a chance there, or even for the third paper for Marwan Yassin, for the questions on the third paper. If not, I'm going to come up with a few there. Okay, so for the second paper there, one thing, there were 6 different algorithms that were chosen for the classification tax. I was curious how they may have differed with respect to computational and data needs, or was that mentioned in the paper? Ali, will you be able to answer that one?
Yeah, I can try. Those algorithms are chosen just randomly. Like we were more interested about decision tree type algorithms, so that it will be more maybe more explainable. The main thing is that we wanted to have some working system for this kind of soil classification, and we wanted to make it available online. So this software is available in GitHub, and you can find the link in the paper. But in terms of computation power, we did not do much analysis in that direction, because it's all about training. So, but the classification part should be fast enough.
The training time. So there, it might be interesting to know the
different
trade-offs, in terms of the training time.
Yeah.
So,
but we did not do any detailed analysis in
something else for future research. Perfect.
Yeah.
Okay. So you can see I'm powering through some quick questions, so we have time for everybody gets covered in terms of Milan. In terms of the 4 soft skill groups, I know you elaborated on them as well. Were there other beyond those 4? Had you considered a variation of that other question I posed? Were there 5th and 6th groups that you had considered but didn't go on, didn't explore?
Yeah, well, actually, there were a bit more, but they were judged a bit too detailed for the amount of data that we had to annotate for learning. So we kind of regrouped them into 4 major categories.
Yes, and having smaller number of categories makes it a bit easier to work with too. Yeah,
exactly.
So I can appreciate that. Any questions for on our final paper here from the audience in general?
Yeah, I have one question.
Yep. Go ahead, Julien.
You tried a random forest, I think, on your data, and I think I saw a very interesting performance for this algorithm. Did you study why this kind of algorithm perform well on your data, or just
because LSTM and GR actually good for the sequential data, and this data actually kind of not too much complex in terms of the ups and down thing. Okay. And that's why the LSTM and GR is giving the good predict the good thing, good prediction. But if it is a complex, our expectation, if we implement to other complex data for multiple time series, maybe it will DPR and deep state will work better than LSTM and GRO.
Okay. But for random forest, you don't have any because it's the data is simple, I think.
Yeah.
Okay.
Yeah.
That's great. And we have time for one more quick question from anyone. Steve, go for it. Or that's why you've turned on your camera.
I don't have a question. I just wanted to make sure that everyone knows there's still one talk to go in the main room in about 1 minute's time. So Keith Yoon is going to be talking to us. So I'll leave you to ask one last question of one of the participants here, but just make sure you head back to the main room instead of leaving right after.
Oh, okay. Thanks for that reminder there. So not to go to gather down afterwards.
No, exactly. No. And we'll be doing awards starting at 5:30, but at 4:45 we'll have one interesting talk about.
Okay, and it's 4:45 now. So you see, you had the final question.
Oh no!
Merci tout le monde.
I took up all the time. Are there any other questions?
No, I think we got to them all. So thank you very much to all the presenters today, and some very interesting talks. Bravo, and looking forward to seeing you in the main room. Thanks.
Right.
Merci tout le monde.
Take care, everyone.